by Fabian, and he'll talk about Calabi-Yau and SU3 structure metrics.
All right, thank you very much. Thank you to the organizers for inviting me and giving me the opportunity to present my latest research paper here. We have already heard a talk on this by Challenger, and I think tomorrow there will be another talk by Mike on this. So I apologize for sort of telling you the same thing over and over, but we have different approaches and it might be interesting to see and how they compare to one another. And I think the fact that we have these, that many people sort of are putting out results on this now demonstrates that this is an important problem in physics or in string theory, which many people have been thinking about. So the work I'm going to present came out at the end of last year, and it's a collaboration with a group in Virginia Tech and a group at LMU. Furthermore, results will be based on a older paper which appeared in 2018. So this will be the SU3 structure part, and this was done with Magdalena Lafos in Sweden and Andrew Lucas in the UK. Okay, so here's the outline. I will start with a brief introduction to string compactification and Calabi-Yau manifolds, and then I will present our results for learning Calabi-Yau metrics and SU3 structure metrics. So given that this is a machine learning and algebraic geometry conference, I'm very happy that I do not have to explain the algebraic geometry behind it or the machine learning behind it, but I do not assume that everybody is familiar with string theory, so I will sort of very briefly give a review about that. Okay, so let me start with that. So from a physics point of view, string theory is a very promising candidate to be a unified description of general relativity and quantum field theory. And this is all based on the assumption that you, instead of having point particles, you have one-dimensional extended objects, strings, which vibrate and then carry or mediate forces, and their excitations, or the ground states in their excitations, correspond to the different particles we observe in our universe. If you do that, and you study the consistency conditions of superstring theory, you find that you require 10 space dimensions. And since you only observe 4, this means that 6 out of these 10 dimensions have to be small and correspond to some compact manifold. So the strings can be open or closed, and open strings sort of end on submanifolds that are called D-branes, and closed strings can just sort of close into themselves. An additional data that you can use to define your string theory is to include a non-trivial curvature of your gauge connection. This is then described by sheaves or by vector bundles over the manifold. So to summarize, the data that goes into a string compactification and that governs the physics that comes out of it is the topology of the manifold, the presence of branes in which devices or curves or whatever submanifolds it wraps, and the presence of gauge fluxes, which are encoded in vector bundles. So as a physicist, you typically want to preserve some symmetries, and supersymmetry is usually chosen as the one to preserve because that makes many computations much more easy. And this means that in order to have this generator of this symmetry, your compactification manifold has to have a special property. So in this case, it needs to allow for a covariantly constant spinor. And the physics equations of motion then put constraints on the compactification manifold. So in this case, it is known that the metric on the compact space is required to be Ricci-flat. And the vector bundle you put on this Ricci-flat manifold has to be slope stable. So this is where the Calabi-Yau manifolds enter the game. And if you look at the Debye cohomology of these manifolds, you find that they are very constrained. So for example, you only have essentially these two numbers are independent, H11, and they parameterize the dimension of the Kähler moduli space, and H21 parameterizes the dimension of the complex structure moduli space. The fact that you have zeros here is sort of telling you that the manifold has exact SU3 holonomy and that you only have one parallelizable spinor. And furthermore, these manifolds have a unique 3-0 form. So what I need out of this is that we have H1 Kähler moduli, H1 complex structure moduli, and a unique 3-0 form. So if you now want to construct a Ricci-flat metric, you essentially just have to set the Ricci curvature to 0, which for a Kähler manifold is given as the derivative of the log of the determinant of the metric, and the metric itself, if you're Kähler, is given in terms of this the derivatives of the Kähler potential. So this is a fourth order partial differential equation, which in principle you could solve in order to find the Ricci-flat metric. In practice, this is extremely complicated because this partial differential equation is very hard. So however, you can make use of the fact that you have a nowhere vanishing holomorphic 3-0 form called capital omega, and sort of wedging it with its barred version, you can build a 3-3 form, just like so. But at the same time, you can use the Kähler form, wedge it with itself 3 times. The Kähler form is a 1,1 form, so you also obtain a 3,3 form. There's only one of them, so these two have to be related. And I just call it sort of the constant that relates into I call kappa. Using this equation, you can formulate a partial differential equation of second order, which is of Morja pair type. This is still very hard to solve, but at least it's second order, not fourth order. So Calabi actually had an important conjecture about the existence of Ricci-flat metrics. Of course, when you want to do string theory, you want to at least know that a metric that satisfies the equations of motion exists, such that we have a consistent theory to begin with. So Calabi conjectured that compact Kähler manifolds with vanishing first Chern class would allow a Kähler metric that is in the same cohomology, or would allow a metric that is Ricci-flat and is in the same cohomology class as a chosen Kähler metric. And he proved that if such a metric exists, it is unique. This is very important because it sort of just gives us a topological constraint which we can check. Checking the first Chern class of a manifold is not very hard. And so since this conjecture is true, as was famously proven by Yau in '77, for which he was awarded the Fields Medal, you have now a very simple constraint, a very simple criterion you can check in order to see that the manifold you chose for string theory actually will give rise to a consistent solution. However, so Yau's proof is non-constructive. It was based on the Morja pair equation, but since it's non-constructive, we do not have an analytic expression for Calabi-Yau threefold metrics. So while we know it exists, we cannot use it in any computations. However, as I said, at least we can build a collection of Calabi-Yau manifolds using this knowledge. So if we sort of look at Calabi-Yau manifolds as intersections of hypersurfaces in toric ambient spaces, we can easily build Calabi-Yau manifolds. So if you just get the complex and the Kähler, you get for free if you do that. And if you choose the degree of the hypersurface such that you cancel the anti-canonical bundle on the intersection, then you know that the space is Calabi-Yau and this flat metric exists. So for the purpose of this talk, I want to focus on sort of the simplest realization you can think of this class of models, which is the quintic hypersurface in projective ambient space of dimension 4. So in general, this is a quintic polynomial in the 5 homogeneous coordinates of P4, but I will look at this family of manifolds, which has one complex structure parameter free here. So since this is embedded in P4, you can take the Fubini-Studi metric from P4 and just pull it back from the ambient space to the manifold. But this pullback metric is not the Calabi-Yau metric, meaning it is not the Ricci-flat metric. Good, so we do have a metric on this manifold, and the 3-0 form on this manifold can also be constructed using techniques that have already been outlined in the late 80s. So we have sort of the Kähler form, and we have the holomorphic 3-0 form. But we don't have the Ricci metric that corresponds to the, or we don't have a Ricci-flat metric, but we have sort of a Kähler class given by the Fubini-Studi metric. So how do we now use this to learn Calabi-Yau and SU3 structure metrics? Well, Donaldson described a numeric algorithm to compute balanced Kähler metrics. These are not Calabi-Yau metrics, but they sort of start from a Kähler potential, which is given by log S times H times S, where H is any Hermitian metric, or is a Hermitian metric that satisfies this condition. This is the balance condition. So H inverse is equal to the product of these vectors S divided by SHS. S itself is a section of a section of OX K1 to K H from 1, where these are the first term classes of the H from 1 devices that specify the Calabi-Yau. So in the simplest case, you take sort of, for the quintic, you just take O of 1. So you just take linear monomials for S, and you take H to be the unit matrix. And in that case, you would get the Fubini-Studi metric. And then, of course, this would be in the ambient space, and then you can just pull it back on to the Calabi-Yau. So in the k goes to infinity limit, this procedure of constructing balanced metrics actually approaches the Ricci-flat metric. So now there is no reference to the Morse-Ampere equation in here, or to the Ricci curvature directly. But it can be shown that if you take higher and higher sections here, this metric, the balanced metric, approaches the Ricci-flat metric. So this was used by Mike and collaborators to numerically approximate Calabi-Yau metrics at some fixed point in Kähler moduli space. So in order to compute this H, there's an algorithm due to Donaldson to compute this, but it's a numeric algorithm, and in order to run it, you need to fix the complex structure in here. But once you have done this, you can sort of just perform essentially a fixed point iteration to find an H that satisfies this H equals H inverse. And in this way, for any fixed K, obtain an approximation to the Ricci-flat metric and sort of an exact solution to the balanced metric. This was already 2006. So then Hedrick and Nasser started from the same ansatz, but they minimized the curvature. Instead of iterating towards a balanced metric, they were now actually trying to get a Ricci-flat metric. And this was done in 2009. And this is in spirit very close to what we are trying to do. So after neural networks had entered string theory in these papers, the topic has been picked up again. So right now, this is 10 years old now. To my knowledge, Young and Anthony and Bird were the first one to sort of use neural networks to speed up Donaldson's algorithm. So they were looking at the determinant of G, and the determinant of G will be essentially J rich J, because that's the completely anti-symmetric thing you can build out of that. And they were using this in order to speed up Donaldson's algorithm too. So to speed up finding these balanced metrics. Then simultaneously with us, Mike and his collaborators use neural networks to approximate Calabi-Yau metrics directly. So not using Donaldson's algorithm, but sort of just using the fact that the metric can be thought of as a map from complex structure manifold, from a point in complex structure space, combined with a point on the Calabi-Yau into a matrix which tells you what the metric is at this point in complex structure moduli space on that point on the Calabi-Yau. And then shortly after, Vishnu, Damian, and Challenger published their work, and Challenger just spoke about this. So in our work, what do? We do include complex structure moduli dependence. We look at cases where we optimize the Kähler potential, which is similar to what Hedrick Nasser did. And we look also at cases where we do not build in Kähler. So we do not start from Kähler potential. So we do not build in the Kähler property, but we are learning the metric directly. And thirdly, we also optimize the partial differential equations which lead to SU3 structure. which are non-Kähler and or non-complex. So if you do this general ansatz, nothing keeps you from going non-complex or from leaving the Kähler condition, because you're not starting with a Kähler potential in the first place. It's something that you impose after the fact anyways. So we can use this for SU3 structure, SU4 structure, G2 manifold, you name it. You just sort of think of it as a continuous optimization task of a partial differential equation, where you're interested in where sort of the solution to this PDE is the function that solves this PDE is the neural network. Okay, so these two approaches, sort of learning the Kähler potential, learning G directly, both have ups and downs. So if you learn this Kähler potential, and learning the Kähler potential essentially means learning this Hermitian matrix H, because the Kähler potential was log S times H times S. So this has the advantage that, of course, the metric is Kähler, since you're starting from a Kähler potential, and it is well defined on the overlaps if you choose these S to be sections of line bundles. But the number in S of these sections grows rapidly. In fact, due to Bott's formula, it grows binomially. Of course, then when you sort of are interested in a section basis on the Calabi-Yau, you lose some, but still it grows like a polynomial, sorry, like a binomial coefficient. And this means then that this matrix H, which is an S times an S matrix, grows extremely fast. You can get around this if there are symmetries. So if the entries in H are sometimes related by symmetry, and in particular for the matrix I showed, for the hypersurface I showed you, there's a lot of symmetry, so this H doesn't have many independent coefficients. But if you just are interested in a generic Poynting complex structure moduli space, this H will have all its independent components populated, and you will have to sort of compute an S times an S, or at least sort of the upper half of this Hermitian matrix. Moreover, of course, Kähler is built into the construction, so you cannot go to non-Kähler manifolds. If you learn G directly, well, you don't impose Kähler, so you need to impose this as in addition to the Monge pair laws, and you also need to make sure it's well defined in the overlaps. However, sort of if you are interested in a 3x3 or in a complex threefold, your metric is always a complex 3x3 object. So you're not plagued by this exponential or by this binomial growth in this matrix H. And you can generalize it to other manifolds. So essentially the path we take is, if we compute G directly, we just make an ansatz for the neural network. We input the point in complex structure moduli space we're in, we input the point on the Calabi-Yau where we want to know the metric at, and then we just repeat this for different complex structures and for different points on the Calabi-Yau, and we minimize the overlap loss, the deviation from being Kähler, meaning that dj is not equal to 0, and the Monge pair loss. And we just iterate this until we are satisfied, and then this will, of course, give us, then if they were all perfectly satisfied, we would have found the unique Calabi-Yau metric. If we take the road of computing the Kähler potential, we make the ansatz for the Kähler potential S times H. We start from a random H, and we compute a section basis S on the Calabi-Yau, and then either we compute a balance metric using Donaldson's algorithm, and using the fact that this approaches the limit in the limit where I take K, sort of the dimension of this monomials in S to infinity, that this goes to the Ricci-flat metric. So I construct sort of just many approximations for Calabi-Yau metrics, and then I use the neural network for regression of H. So meaning I learn the complex structure dependence by constructing Ricci-flat metrics or balanced metrics for different complex structures, and I just phrase the fact that I don't know the complex structure dependence as a regression task for a neural network. Or I optimize H directly to minimize the Monge pair loss. And again, in both cases, if I make sort of my section basis large enough, I will sort of converge this moduli-dependent Calabi-Yau metric. So let me go through the first line here. So as a starting point, we start from the pullback of the Fubini study metric, and we learn the Calabi-Yau metric as a correction to that. And there are essentially two ways, or many ways you could have done this. You could have just said that the Calabi-Yau metric is given by the Fubini-Studi metric plus the correction from the neural network, or we take it here to be the sort of this multiplicative correction. So it's the Fubini-Studi times 1 plus the neural network. So we're only learning this, and this will correct the Fubini-Studi metric to produce the Calabi-Yau metric. Sorry, how much time do I have?
You have another 15, 18 minutes.
Okay. Okay. The watch is not working. That's a problem. Thank you.
Yep.
So we then tune the neural network such that the metric satisfies at all the points we feed in during training the overlap condition, meaning just that sort of going from patch I to patch J, you have these transition functions. So this will give you sort of a metric, a matrix, and then we just compute this in different patches, and we subtract this and we sum over all the points here and take the mean squared error. Then we have the Kähler condition, dj equals 0. Again, this has many different terms of the form, well, for example, this daj will be of the form da jij bar minus di da ja bar, and we just sort of again sum over all the terms that sort of appear in dj equals 0 and take the mean square of that. And thirdly, there's the Morse-Ampere equation, j cubed equals omega squared. And in this case, we just compute sort of the deviation of j cubed from omega squared, meaning we look at 1 minus j cubed over omega squared. This should then, up to this proportionality constant, which you can fix to whatever. And so in this case, sort of this is a good value for later for the SU3 structure, but of course, you could also absorb it in one of these quantities here in that case. So we define this measure sigma to be sort of 1 minus j cubed over omega squared. And then we just, sorry, this one should be gone. So, and then we're just summing sigma squared as the Morse-Ampere loss. One thing to note is that typically when you do neural networks, of course, the way you optimize them is you take derivatives with respect to the neural network parameters that parameterize the function that the neural network is trying to learn. In this case, we need to take derivatives, of course, with respect to the parameters of the neural network in order to make it approximate the Calabi-Yau metric. But we also need to take derivatives of the neural network itself, meaning derivatives of the neural network with respect to the input. And unfortunately, this is not as optimized in, well, at least in PyTorch, this was not as optimized as the differentiation packages which you have to differentiate with respect to the neural network parameters, because that's not something that is typically done when you train a neural network. So this was one of the bottlenecks, actually. Then the total loss will just be a combination of the overlap loss, the Kähler loss, and the Morse-Ampere loss, with some weighting lambda I in front. And we just performed a box search in order to fix these hyperparameters. And we chose sort of, sorry, this should be a lambda 3. We chose a Morse-Ampere equation to have the highest rate because we already start sort of with something close to Fubini-Studi. So the overlap loss and the Kähler loss is already small. But the deviation from the Morse-Ampere equation is quite sizable. So we are weighting sort of this stronger so that we converge to a solution more quickly. So to find points in the Calabi-Yau, this was the first step. We just fixed 2 points on the sphere inside P4. Then we find a line through these points, and then we intersect this line with the Calabi-Yau hypersurface. And of course, it's a degree 5 surface, so this will intersect in 5 points. So we get these 5 solutions. We add these 5 points, we sample another pair of points in the sphere, do this again, and just repeat over and over to get a sample of points. Then we set up the neural network. Well, as I said, we just should think of it as being a function from complex structure moduli space times a point on the Calabi-Yau into a 3x3 matrix, which is the metric. So we get 10 input nodes that give you the point of the Calabi-Yau. Then we also input the patch in which we evaluate the neural network. In principle, this could be a single number from 0 to 4, so you can cover P4 with 5 patches, sort of where the ice homogeneous coordinate is non-zero. But we sort of use this as a one-hot encoding. So we use a 5-dimensional vector of zeros and ones, and if you were in the ith patch, you had a 1 in the ith entry and 0 everywhere else. And we also input the complex structure point where we compute the metric. So in general, this would be h to 1-dimensional, this input. For the family of manifolds we looked at, this was just a single complex value of psi, so 2 real coordinates. The output of the neural network then is just the metric. So this has 3 real degrees of freedom on the diagonal and 3 complex off-diagonal degrees of freedom. So these are 9 degrees of freedom. We played with the architecture. So if this is fixed from the input, this is fixed from the output, we played with the architecture. We found that we do not need a relatively complicated network. We also found that performance doesn't depend a lot on the activation functions. So what I'm showing you here is just sort of a very standard simple neural network with 3 hidden layers with 100 nodes and a leaky reader activation function. So yeah, we tested several hyperparameters. The architecture, as I just explained, increasing the number of nodes, which didn't give you more mileage unless you included more sampling points on the Calabi-Yau. The number of hidden layers didn't have a big impact. The activation function did not. And the optimizer we used also didn't have a huge impact. So I will be giving results for 50,000 points per psi sampled from a box, sort of with between -100, -100i to +100, +100i. We used a relatively large batch size because the data is small, so there's no RAM issue of fitting this into the memory. And we trained it for 20 epochs with an Adam optimized and learning rate of 10 to the -4. So as I said, adding more points will improve the accuracy, and sort of adding more points, it just becomes an exercise in patience. Of finding these points is very, 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 very cheap. But then, of course, you need to optimize over these more points, and this is where the time then goes. We then, we constructed a test set of 5,000 points, and to prevent overtraining, we sort of looked at early stopping, meaning the test set error did not improve, or did not, sort of stayed constant. Then you can essentially stop because the train set error will go further down if your neural network is powerful enough, but you're not getting anything out of it because you're just overfitting. We included dropout layers after the first and or the second hidden layer. We used batch norm layers after the first and or the second hidden layer, and we used an L2 weight decay when we tried parameters for the weight decay from 10 to the -4 to 10 to the -8. So none of this made a big difference either. So in the end, we just sort of didn't include any of these and just used this early stopping criterion. The goodness of the size of the error didn't improve when I did this. I just had to train, or we just had to train it longer than neural network without getting any improvement in accuracy. So here are the results. What you plot is the Monge-Ampere loss, the Kähler loss, the overall loss, and then the sum of the 3. So you can see sort of in the beginning, the Kähler loss and the overlap loss are small. That this is because you're already starting from the Fubini study metric, and the Monge-Ampere loss is pretty big. And then as you optimize, this goes up a little bit. This first goes up a lot, and then in the end, it's up by a factor, I don't know, 1.5 or something. This is up by a factor of 2 or 3, and this goes down by a factor of 6 or something. In terms of the sigma measure, you see that in the beginning, so this is drawn for one specific fixed point in complex structure moduli space, and for this point, this was psi equals 10, you have a sigma measure error of 0.35. So remember, the sigma is the deviation from the Monge-Ampere equation, so j cubed over omega squared. And then when you continue training, this goes down to something like 0.06. If you wanted higher accuracy, as I said, you'd need more points, and eventually also a larger neural network. But training this longer doesn't improve the test. So this is all for the test set, and training longer didn't improve this. If you sort of chose the other route, you would find the following. So what I plot here is the approach where we did regression for the Donaldson algorithm, meaning we just went to Donaldson algorithm from 20 years ago, computed at different points the metric, and then we did a regression with the neural network to learn the complex structure moduli dependence. And what you find if you sort of do this dense sampling of complex structure moduli space, this is the sigma loss that you get. And what I've drawn here is sort of the result which you get from Donaldson's algorithm at randomly sampled points within this box in blue, the neural network prediction when I trained it in orange, and the nearest value in green. So nearest value means just sort of instead of using any interpolation with the neural network whatsoever, you just take a point that's nearby in Euclidean distance in this complex structure moduli space, you compute Donaldson's algorithm there, and you use this as an approximation for the Ricci-flat metric at a different point in complex structure moduli space. And you see, it doesn't make a big difference if you have this sort of very dense sampling. However, if you do a sparse sampling, so now this is switched to logarithmic scale, and this is a more sensible setup because computing these points is very, very costly, especially when you make k larger, and of course you want to make k larger in order to get closer, in order that the balanced metric approaches the Ricci-flat metric. And you see in this case, if you're in the sparsely sampled regions, the error from using the close by point is huge, whereas the neural network still has learned to interpolate this. So the use case would be if you want to use this to make the complex structure moduli dependent explicit in the Calabi-Yau metric, you would sort of use a fairly high k to sample metrics or to sample different metrics, and then use the neural network to learn for these few sample points to interpolate between them. If we do not do Donaldson's, but more of Hedwig Nass's approach of learning the Kähler potential by optimizing the Morse-Ampere equation, we find a plot like this. So you see that what's plotted in green is the result of Donaldson's algorithm at k equals 6. And yet, since this is learning the balanced metric, there are actually better, meaning more Ricci-flat metrics at the same k available, and the neural network sort of produces a flatter metric than the Donaldson at the same k, which is due to the fact that this is optimizing the Morse-Ampere loss, whereas this is finding a balanced metric. So here it was trained from 10 to 100, and then it was extrapolated up to 1,000, and you find that if you extrapolate out of your training area, your error of course goes up as to be expected, but sort of if you could get away by a factor of 2 extrapolating and still be sort of in the same ballpark as you are if you start with Donaldson's algorithm to begin with. Okay, let me finally talk about SU3 structure metrics. So SU3 or Calabi-Yau manifolds have SU3 holonomy, and they are a special case of SU3 structure manifolds. These become important once you start adding branes and fluxes, because these backreact on the geometry and they can make your manifold non-Kähler or non-complex. For SU3 structure manifolds, we know much less than we know about Calabi-Yau manifolds. There is much more freedom in SU3 structure manifolds, so there are much more SU3 structure manifolds or metrics that have SU3 structure in some sense, but only very few of these are actually relevant for physics, meaning they solve the equations of motion which you get when you include branes and fluxes. So the SU3 structure manifolds can be defined in terms of these 5 torsion classes. You have a fundamental 2 form and a complex 3 form, and you can just write them in terms of one another and in terms of these W1, 2, 3, 4, 5. So if all of these were 0, then the J would be 0 and the omega would be 0, and you would be back to the Calabi-Yau case. And so if, for example, if W1 and W2 are non-zero, then then you're non-complex anymore. If W3, W4 is non-zero, of course, you go away from Kähler and so on. So you can sort of classify the properties that your space has based on these torsion classes. So if you solve the physics equations of motion, you sort of get a constraint on these torsion classes. But these torsion classes is not sort of an input you can choose. When you choose your manifold, you choose J and omega, and the torsion classes are derived quantities. So the problem is sort of you then have to guess an ansatz for J and omega, you compute your torsion class, and you see whether it's something that actually is relevant for string theory. Even though you know what you want to get from string theory, but you have to start with something else and then derive these quantities and check. So one set of torsion classes that is relevant for string theory, for example, is W1 and W2 equals 0, W3 is whatever, and W4 is 2W, W5 is 2W4. This is the so-called Hallström system. So now in this paper 2018, we derived an analytic expression for SU3 structure metrics, meaning we gave an ansatz for J and for omega and how to modify them. So with J, we just start with the Fubini study metric, the pullback of the Fubini study metric. That's of course the Kähler. We started the holomorphic Calabi-Yau threefold omega. This is of course still closed. And then we modify it by some function f. So f is just a function. We take its kth power. And sort of by this modification, we now generate non-zero dj and non-zero d omega, such that omega 2, omega 1, and omega 3 is 0, and omega 5 is 2 omega 4. So we give an analytic expression for this f. So meaning you now have an analytic expression for j and with this for the metric. So in this case, sort of we have an explicit analytic SU3 structure metric, and we have something to compare the neural network result to. So we set up the neural network to sort of to learn this. Instead of dj equals 0s, instead of the Kähler condition, we now input dj is equal to omega 4 wedge j plus omega 3, well, omega 3 was 0. And for d omega, we input omega 5, w5 wedge omega. And we optimize this instead of the previous conditions. Again, we find sort of that the Kähler and overlap loss are small in the beginning. The deviation from j cubed equals omega wedge omega bar is large. As you go on training, this significantly improves. And in the end, so we have a good approximation to the SU3 structure metric. And in this case, in contrast to the Calabi-Yau case, we could actually cross-check against our known solution, our known analytic solution. So we cross-checked the eigenvalues of the metrics, and they agreed within 10% or something, the smallest and the largest. Okay, let me conclude. So neural networks can learn moduli and position-dependent Calabi-Yau metrics by optimizing the underlying differential equations, as we have seen. Meaning, we now have a way of phrasing this just as a continuous optimization task and obtaining these types of metrics. And this has very many important applications. Physics, for example, we can use it to compute massive string excitations, can use it to check swampland conjectures, which are conjectures of what happens to the physics as you move large distances in complex structure moduli space. Of course, for that, you will need knowledge of what the metric does when you move these distances in moduli space. You can compute Yukawa couplings. You can apply it to math, for example, the SYZ conjecture, which says that Calabi-Yau metrics are T3 fibered, and if you take a limit in complex structure moduli space, this fiber shrinks to 0 size. And you can, so if you have the metric, you should be able to see this. And lastly, our ansatz generalizes to SUN or T2 structure manifolds. And I've given you a particular example here where we reconstructed, or we were able to show that this goes to a known good solution of the Hallström system. Thank you very much.
Thank you very much, Fabian. And so we have time for a question.
Can I ask a question?
Sure, go ahead.
This is Andre Lucas. Hi, Fabian. Sorry, I think I've asked you this before, but I've forgotten the answer. In the case where you where you compute the metric directly, how do you feed in which Kähler class you are computing the metric for?
Good. So yeah. So just to provide a little bit more background to the question, if you write down the Kähler potential, sort of there is this there's a parameter, the Kähler parameter, that parameterizes the Kähler moduli space. So this H11 for the quintics of 1, and your question is, where's this 1 in this case? Well, if you sort of, this 1 is hidden inside this constant kappa here in some sense. You can rescale omega and j, you can just shuffle it back and forth in this particular case.
Yeah, sorry. Yeah, for H11 equal 1, yeah, that's right. It just scales. If it was 2, for example, what would you do then?
If it was 2, then yeah, and that's a good question. I actually hadn't thought about, because we applied it to the H11 equals 1 case. So if I had to guess now, probably you would still have a fixed omega, and then you would have sort of probably just a relative scaling between the two.
I mean, I'm kind of wondering if in that case you would have to impose a fourth condition, which kind of says the cohomology class of the metric equals something fixed.
Yeah, that's a possibility. Yes, you fix the cohomology class of the metric for which you want to have the Ricci-flat metric of, and then you optimize to get this to get the metric in this cohomology class.
Okay, thanks.
Great. Let's thank Fabian again.
Thank you.